When a digital experience stalls, the delay feels physical. You are requesting information, and somewhere along the pipeline, a massive object has slammed into a narrow corridor, wedging itself tightly and blocking all forward movement. This browser architecture diagram illustrates the technical reality. When a server sends a monolithic 5-megabyte JavaScript payload, that single massive red data block wedges directly into the main thread, immediately halting all smaller, subsequent processes trying to pass. That blockage interrupts the critical rendering path. This is the mandatory sequence a browser must execute to construct the document object model and the CSS object model. Until that path clears, the user sees an entirely blank screen. The structural optimization strategies and architectural data we will use to dismantle this blockage are provided by Royal Research. Front-end performance is dictated by 3 strict measurable variables: network latency, browser rendering speed, and server response time. To achieve near-zero latency, we have to isolate those variables and systematically dismantle a monolithic application payload using structural first principles. A sluggish site is a measurable structural failure. Waiting for a blocked pipeline empirically drives up bounce rates, kills user engagement, and actively degrades search engine rankings. The worst-case starting point for any application is transmitting an unoptimized, heavily bloated text file of human-readable source code directly from the server to the client. The first corrective step is subtractive. We apply minification. This diagram shows the minification process in action. Build tools like Uglify.js and CSS Nano strip out every piece of whitespace, every line break, and all developer comments. The formatted structure collapses into a dense, unreadable, single-line brick of text, leaving only the executable logic. We then apply a secondary layer of file size reduction, compression. Using the gzip algorithm, that dense logic brick is squeezed into a highly compact package specifically for network transit. Minification permanently alters the code by removing unnecessary characters. Compression temporarily packages that code so it can travel faster over the network. The file moves rapidly across the wire, but upon arrival, the browser still has to unpack, parse, and evaluate the entirety of that heavy file before executing a single command. Shrinking the payload is a mandatory baseline practice. It reduces bandwidth, but it fails entirely to solve the browser's execution bottleneck. The main thread is still receiving too much logic at once. Single-page applications historically solved interface routing by sending the entire catalog of application logic in one massive initial download. This guarantees an execution bottleneck. The structural solution to a monolithic codebase is code splitting. This animated diagram illustrates modern JavaScript bundlers like Webpack or Parcel. They automate the division of a single codebase, slicing the main bundle into logical, distinct modules. Here, we see an entry point separating from distinct interface routes. By utilizing dynamic imports, the browser requests only the specific module required for the user's current view. The entry point loads immediately, while the logic for unvisited routes remains stored on the server. Minification shrinks the text size. Code splitting changes exactly when that text is permitted to load. The immediate physiological benefit to the application is an unblocked main thread. By processing less JavaScript on the initial render, developers drastically reduce the time to interactive metric. Segmenting the code into smaller, chunked files also yields higher success rates for browser caching when users return for subsequent visits. By strictly enforcing that the browser evaluates only the logic immediately necessary to render the current screen, developers bypass the primary rendering bottleneck entirely. Once the executable logic is split and upped, high-resolution images and embedded videos consistently rank as the heaviest payload items on a web page.
Lazy loading is the strategic deferral of these non-critical visual resources until they are required by the user. The critical boundary is the fold, the bottom edge of the user's initial screen state upon first loading the page. Anything below that line is unseen. This animation demonstrates the simplest modern implementation. By applying the native loading equals lazy attribute to an HTML tag, the browser leaves a placeholder. As the user scrolls and those empty frames cross that threshold, the browser initiates the network request and populates the image. For complex interface interactions, developers use JavaScript intersection observers. This establishes an invisible trigger zone below the active screen, initiating the data pulse slightly before the user's view reaches the element, ensuring the image is ready the moment it enters the viewport. To clarify the distinction, code splitting strictly manages background executable logic and JavaScript. Lazy loading specifically handles the physical media and DOM elements rendered to the user. Lazy loading optimizes the network. The user never pays the bandwidth cost, and the server never pays the transit cost for content the user hasn't actively scrolled to see. With the payload minimized and the rendering path cleared, we encounter the final constraint of the internet, the physical speed of light and geographical distance. This globe illustrates the severe latency penalty of geography. If an application runs on a single centralized server in New York, a user requesting data from Tokyo must wait for packets to traverse the entire physical distance of the Pacific Ocean. Content delivery networks solve this by distributing mirrored copies of the application to localized data nodes, called edge servers. The New York origin server places a copy directly in Tokyo. The local user pulls the data instantly from Laron City. Global server distribution minimizes transit time. Browser caching eliminates it entirely by storing the data locally on the user's own device. Developers dictate this local retention using server-side HTTP headers. The cache control and expires headers instruct the browser exactly how long it is permitted to store and serve a local copy of an asset without checking the server. Aggressive caching carries a specific risk. If the developer updates the application logic, but the user's browser continues to serve the old, locally cached file, the interface breaks. The standard solution is cache busting. Developers append unique version numbers or randomized hash strings to the resource URLs. When the code updates, the file name changes. The browser recognizes a new string, ignores the cache, and downloads the precise updated file. CDNs and precise caching strategies artificially eliminate physical distance. They guarantee that repeat requests happen with virtually zero network latency. When we combine these subtractive and deferral techniques, we restructure the application's entire delivery mechanism. This split-screen network waterfall chart visualizes the contrast. On the left, the legacy monolithic architecture blocks the pipeline with a single, massive execution request. On the right, the optimized pipeline operates as a rapid cascade, chunked logic, deferred media, and cached assets clearing the path in fractions of a second. Advanced architectures take this one step further with prefetching and preloading. The system downloads necessary assets in the background, anticipating the user's next navigation click before they even make it. Optimization is never based on a visual approximation. It must be empirically verified. Developers use diagnostic scanners like Google PageSpeed Insights, Web Page Test, and Lighthouse to measure hard metrics, ensuring the time to interactive and first contentful paint numbers align with the newly optimized architecture. A sluggish website is not an inevitability of modern web development. It is the direct result of unoptimized, default architectural choices. By utilizing the structural data and optimization strategies provided by Royal Research, developers can precisely dictate when and where resources load, replacing bottlenecks with speed, efficiency, and zero latency performance.